from last time was the distance formula. The analog of the distance formula for the plane dimension 2 Cartesian system is the formula is here somewhere. Here it is. Okay, so simple rule. It's not as complicated as it might seem if you just remember that picture over there at the top. So it's just a form of the Pythagorean theorem. It's not as easy in dimension 3 because there are 3 dimensions, so Pythagorean theorem does not apply directly, or rather it does not apply once. You have to apply it twice in order to come up with the formula. Fortunately, it looks very similar to the 2-dimensional case, just an extra term. So you can see 3 terms here for each of the 3 coordinates, for 2 terms for each of the 2 coordinates, and then you'll have three terms when you have 3 coordinates. You have 4 terms when you deal with the 4-dimensional space, and so on. Okay, so let me point that out. That is the picture that I was referring to. I have the dimensions of the box listed here on the left, those absolute values, and then in 2 steps I will discover what I will find. First, this length over here based on the distance formula, or the Pythagorean theorem if you prefer, from before. So this length is, what is this length? It is so in other words, I take one face of my box. I'm looking for the length of the diagonal of my box. So I do it in 2 steps. I first find the diagonal on the side of the box. So that's what I was just looking at. On the far right, I have left the rest of the box out of it for the time being, so that my situation has become 2-dimensional again, and we know how to handle 2-dimensional situations. So the distance here is 2 sides, y and z, so it will be y minus y prime squared plus z minus z prime squared. What does it give me? Let's call this diagonal d. So by the Pythagorean theorem, the square of the diagonal will be the sum of the squares of the 2 sides, and those 2 sides just happen to be the differences of the 2 coordinates of the 2 points. So 2 points, 2 out of 3 coordinates we take into account, and we get one of the diagonals. So concentrating only on this box, on this side of the box, this one, the one that faces us. Okay. So once we have found that diagonal, now there is an extra direction that happens to be x. So we are progressing in this direction like this along the x-axis towards us. And then the diagonal that we're actually interested in is this green one, right? Okay, so we are seeing it here, and this time we are in a better position because we have a triangle. We still, once again, we had a rectangle, 2-dimensional thing. Now, after some work and a single application of the Pythagorean theorem, we have our diagonal, and now we forget about everything else. So we forget about those that face we just paid attention to, and we concentrate on that triangle over here. And what is that triangle doing for us? We know its sides. Well, rather, we know the side D, and we know the red side, which is simply the difference of the x-coordinates of the 2 points. Okay. So the good news that's not enough. Fortunately, this triangle is also a right triangle. So this is a 90 degrees angle over here. Okay, so then we have a Pythagorean theorem again. So if we are after this distance, ultimately the distance between the 2 points, this is d, distance between 2 points P and Q with those coordinates. So what is the d? D squared is, based once again by the Pythagorean theorem, d squared is equal to d lowercase squared plus x minus x prime squared. Okay? And that pretty much takes care of everything, because now we substitute. We have the substitute in my distance d squared, the diagonal distance, is in fact, what is it? X minus x prime squared plus y minus y prime squared plus z minus z prime squared. Okay, so and that is the formula for the distance of the between these 2 points. Okay, so that is, you can think of this as the distance formula. I don't like to necessarily put that square root over there. It's not crucial. You can always take square root whenever necessary, but that's why this formula is preferable, the one without the square root. Not only it's less cumbersome, it helps you to remember that this is about the Pythagorean theorem. Technically about 2 Pythagorean theorems applied consecutively, as we just did. Okay? Okay, so so that is why we care. Well, we now can do geometry in the 3-dimensional space, but in the spirit of that our yesterday discussion, we can also use it to represent certain geometric figures algebraically. In particular, the sphere. Okay, so remember yesterday we talked about the meaning of the word circle. Okay, and a circle means on the plane it is the all the points within, say, circle radius 1 centered at the origin is the set of all points 1 unit away from the origin. Okay, so that's the circle, and now we're using the same language, identical language, in order in 3-dimensional case. So let's once again let's do it this. So dimension 2. The circle of radius r centered at point, say, O, is or consists of all points on the plane r units, exactly r units from O, from the origin. Okay, so like this. This is O, and every single one of them is exactly r units from the origin. Doesn't matter what that point O is, and doesn't matter what that R is, as long as it's positive, we're going to end up with a circle. And here we also technically have to be careful about what we mean by the circle. We do not mean the inside of the circle, but only the curve itself. Okay, which makes it somewhat ambiguous, or rather questionable, the terminology that we have used previously. For example, we computed the area of the circle, which is, isn't right, because we are talking about the circle. Technically, it is not the disk. So that's a circle. This is a disk. Well, yeah. So what if it includes everything inside? We would rather call it a disk. Circle on the left and disk on the right. So if we're talking about the area of the circle, we're actually talking about the area of the disk. So curve does not have any area in itself. It might enclose area, and that is the relation between the circle and the disk. Okay, and now what happens in dimension 3? Not much different. So if I go on and take the same wording, but in dimension 3, so instead of a circle radius r, I will be talking about the sphere of radius r centered at a point O, consists of all points in space, 3-dimensional space. Well, I probably shouldn't cancel it. So space r units from O. Okay, so the picture is almost the same, except you are not limiting yourself to the plane. So you certainly can make that point like this is a piece of paper, which makes it a plane. Or if we do not have a plane, that you can go not only horizontally but also vertically and in all kind of diagonal directions. So then the result will be this. So that's my center over here, and I could look at the radii in all directions like this. So what I have drawn here, an extra circle in the middle, that's like the equator. Equator, and then which is a circle, by the way. And in the center of that circle is also the center of the sphere, and that is from that point you can measure distances in all directions. Okay. So and then the same controversy here is what to do about the difference between the sphere, which is a surface on one hand, and a cannonball, or just a ball, which is filled with, well, it's filled like a cannonball, rather than a ball which is empty. Possibly that's what sphere is, but it is whatever the whole solid that is enclosed by the sphere. Okay, so once again, this is a sphere, this is ball. That's actually a term that is normally used in mathematics when we're referring to things enclosed by spheres. It's called a ball. Okay, so various, and then you can speak of, then the language also changes. In the two-dimensional case, we can speak of the length of the circle, and we can speak of the area of the disk. On the other hand, in dimension 3, you can speak of the surface area of the sphere, and we can talk about the volume of the ball. Okay, so we already know how to handle volumes a little bit. We actually computed. No, we didn't. Did we compute the volume of a ball earlier? Yeah, we did. Right, we did. Right, the cross sections. Remember, so cross sections, they're circles. You can see them if you start crossing it like this. You will see more and more circles, and then you integrate the area function, and you get the answer. That's how we got it. There are other ways, but for the time being, we're just looking at it for what? Just a matter of how to represent these two side by side. So we already know that for the circle it is x squared plus y squared is equal to r squared when the center is at the origin. Okay, similarly, well, where does it come from? It comes from the distance formula, right? That one comes from the distance formula. So what is the distance from point 0, 0 to point xy? Well, that's what it is. So this is the square of the distance from 0, 0 to xy. Okay, so, and now we are in a very similar position because the definition of the sphere and the circle is virtually identical. And so then what we're interested then is in square, once again, square of the distance from 0, 0, 0, that's where we place the center of our circle, to xyz. And what is it equal to? X squared plus y squared plus z squared is equal to r squared. Okay, so everything goes in parallel as you go from dimension to the next. Here we went from dimension 2 to dimension 3, and some language is very similar. So we're talking about distances, we're talking about locus, a collection of points satisfying certain properties, which incidentally is not that easy to plot. If you think about it, these are called, by the way, implicit equations. Okay, so what does it mean? It means that the variables are related to each other, x, y, and z, or just x, y, but it is done implicitly. So y is not explicitly expressed in terms of x. Okay, so that makes it problematic because we cannot easily plot the circle in that manner unless we solve for y, which we could do and we have, but think about case, the three-dimensional case, then we would have to solve, for example, for z, and that once again it might be a problem because that creates a function of two variables, so which we'll have to face sooner or later. But we'll see what we can do until then without that. We have found a new representation. We have found a representation for the sphere. Okay. Incidentally, what is the representation of the disk and of the solid ball? So if the circle is given by that equation, what's the representation of the disk? Well, how would you describe the disk? So look at the circle. The circle of radius r consists of centered at 0, consists of all points on the plane exactly r units from 0. That's the circle, like this. What about the disk? The one that also contains everything inside of the circle. How would you describe it?
Maybe all points including and within the r.
Can you express it in terms of distances?
All points within r.
That's right. The distance from that point to the center should not be larger than r. Okay, so that if the center, this is less than r, right? This distance is less than r. So if you go all the way to the circle, to the edge of the disk, then it is exactly r. But all the points will be within r, no more than r, starting from 0 and all the way to r, which means that what should I do to that equation on the left to get the disk? I just replace equal with less than or equal to. Okay, so the disk is represented x squared plus y squared less than or equal to r squared. Okay, so once again, all the distances from point 0, 0, 0 to xy is less than or equal to r. That's what this statement says. Similarly, with the solid, it will be x squared plus y squared plus z squared less than or equal to r squared. Okay, so that is our representation. Well, there is one more. There is one more interesting example here. Is what if I take my equation of the sphere, of the circle on the left, and that one, this one, and I take it to the right. So here's my question: what is x squared plus y squared is equal to r squared? Well, let me tell you right away, it's not a circle, and it's not a sphere. Why it's not a circle? Because it lies in the three-dimensional space to begin with, and it's not a sphere because we already have the equation for the sphere, so that's not a sphere. So what is it?
Would be a plane with a 3D object.
No. What about what is the meaning of x squared plus y squared in the three-dimensional space?
Is it r?
What?
The radius?
No, r is still the radius, yes. But I'm trying to come up with an interpretation, a geometric, verbal interpretation or description of this formula. So the distance to the origin is x squared plus y squared plus z squared. If I drop z squared, what do I get? What is the distance to? I have point x, y, z. What is the x squared plus y squared is? What is it? Well, let me plot it for you. What?
Is it r squared minus z squared?
No, x squared. No. Like I said, this is not the sphere. Okay, so the sphere is just one of our possible surfaces that we can think of in the three-dimensional space. So the simplest one, the next simplest after the plane Okay, but now let's forget about it. We know that what we're talking about right now is not a sphere. So the distance is, in fact, as if it is measured entirely. Look at it. It's as if measured entirely within the xy plane. So this is my point over here, x, y, z. But the distance is measured how? Like this. You see? Right? So point x, y, z hovering above the xy plane. But the distance measured along in a horizontal way, like I showed there. It's going not towards the origin, but rather to what? Z-axis. Which we just did when we derived the equation for the sphere. That's what we did a minute ago. Okay, so once again, the that thing over here is this: the distance from the my point x, y, z to the z-axis. Okay, right? You see, x squared plus y squared. Well, it's not equal to, but rather it is squared, but close enough. So square root of that thing gives me that distance. Okay, so if my distance to the z-axis is fixed, what am I getting? All the points are units from the z-axis. What is it?
Cylinder?
It's a cylinder, right? So you can detect it entirely if you limit yourself first to the xy plane, and then you realize that this equation does not contain z. What does it mean that you are in a three-dimensional space? You have three variables, and yet one of the variables is missing. It means that it is arbitrary. What does it mean? It's arbitrary that you can freely move vertically without changing anything. So if, for example, if you start with the circle on the xy plane here, like this is the circle that we just talked about. That's the same circle as this one. Okay? Because the equation is the same. And then turns out that this is the only restriction on x, y, z is that x and y have to belong to x, y belong to that point, belongs to the circle of radius r centered at 0. So the one that I plotted there. But then what's the restriction on z? There is none. So it means that we can go up from the circle, up or down in the vertical direction like this. Up, 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 and altogether what happens, I have created a cylinder. Okay? So that gives us one more example of interesting surface for us to study in the three-dimensional space, in addition to the plane or planes, spheres, and now the cylinder. You can see also how much more is happening in dimension 3 in comparison to dimension 2, because not only we have one surface, that we have surfaces to begin with instead of just curves, and surfaces are more complex. And then we have different kinds of surfaces, as you can see, not only like spherical. There is a parallel between circles and spheres, but there are no parallel, or at least that I can think of, for the cylinder in the two-dimensional case. Yeah, there is nothing interesting there, I don't think. So, okay, so the point with this, so we're going to be in three-dimensional space. We will be computing two things, well, actually three things: lengths of curves, areas of surfaces, and volumes of solids. Okay, so that's the three things we do in dimension 3, and naturally, if we are still in dimension 2, we instead of 3 have two things to do: lengths and areas. So you can see how more and more things you can do. So what I want to do now is to do something very basic in fact in dimension 2. In dimension 2, let's do something very basic, and that is the length of the circle. We know the area of the circle. We did it, right, from scratch. We did it with approximation as well as with integration. So now the time has come for the length, the circumference of the circle. Okay, we have all we need. Okay, so what do we need? well, this is all we need. That formula over here will give us approximations of the circle. So we'll go from one point to the next. Well, let me just go straight with Excel and do it. Okay, so this one we've seen before. This is how we computed the area of a circle. Okay, so as you can see, the first you have x column, x values, y values are computed by the familiar formula 1 minus x squared, square root. Okay, so and then we created well, that I don't think we need this. Let me just delete this here. Okay, and then we computed the areas of those bars. Okay, and then if the step was small enough, 0.1 or 0.05, then we ended up with a number that is pretty close. So this is our result of our computation, the sum of these areas. And over here, the result is the exact result, which is pi over 2. It was very close. Now we are taking the same representation, so the function will be the same, but we are not concerned with the area anymore. Okay, so what I'm going to do is, well, oh, here it is. I already have it somewhere. I didn't realize, but in part this is what I'm talking about. This is what we're after. We're after the curve. It's not a curve technically. We're just a bunch of points, but it's good enough. So why is it only half? Let me stretch it out. Okay, so this is of no interest to us anymore. So I'll move it away, just out of the way. But remember that's where our previous experience. And why is it not incomplete? It's just missing one point, I guess. Yeah, I'm afraid I'm going to need this. Well, I guess maybe not. It's okay. So actually, the error will be somewhat significant, but I'm afraid we just don't have a choice about that. So as you can see, the last leg will be missing. That part will be missing, which is pretty large. The same edge that I have here is missing at the end. Why is it?
You have a point for x equals 1?
Why don't I just did, but for some reason it gave me division. It's square root. I guess this is not entirely accurate. So I'm doing square root of, it's supposed to give me 0, and it doesn't give me 0. It's supposed to be 0. Look at it. If I substitute 1, this is the formula. I substitute 1, it's supposed to give me 0, but it's never entirely accurate. And so that number that is giving me is not 0. So, well, let me just, make an executive decision here and put zeros here. Well, I will delete areas. We don't care about areas. Okay, so areas are going away. Okay, so the plot, let me finish. The plot is missing one point, so I want it. Okay, so the difference, as you can see, the Excel does it all for you. For areas, we have bar chart. For curves, we have a scatter plot over there. Okay, so but it's only visualization, obviously. Our computations really does not rely on that at all. So instead of areas, I'll have what I'm going to have here, lengths. Lengths of what? Of each of these segments. You can see those segments, right? Those the points are plotted. These are the only. Each of these is just a point. Each pair of numbers is a point. That's the Cartesian system of dimension 2. And then so they're plotted, and then Excel connects them by curve, which is really just for it to look pretty. But it's entirely just points, nothing else. Okay, so we have the lengths. Let's compute the lengths of these segments. Okay, so I have these four. These are 2 consecutive points, and I will put over here its length. So the formula, we have the formula. I just type equal to what? The distance formula, dimension 2. square root.
X minus x prime squared plus y minus y
Right.
prime squared.
So this, okay, another parenthesis, this minus that parenthesis squared, okay? And then the same for y, so that's the difference of coordinates, x coordinates squared, and now difference of y coordinates squared, okay. Like this, and now I'm subtracting y's, minus that, parenthesis squared, and another parenthesis to close the whole thing up, okay? See the formula, right? It looks a bit more complicated than the algebraic representation, but that's what happens when you do use Excel. It's a little bit more cumbersome than we're used to. Okay, so that is the length of that longer leg over there, 0.31623, and then I just expand them all. Okay, so these are my lengths of legs. As you can see, start pretty long, then becomes shorter and shorter and shorter. At the top, it's very small. So it's actually our approximation is far from perfect because it's so non-uniform. Ideally, and that's done usually in calculus 3, you approximate it in a more uniform fashion per angle. This approximation is per value of x, intervals of x. We're moving on along the x-axis. You can see in the column for x. We're moving a little bit at a time, and which means that at this point we have a big jump of y. Small step for x every time, but for y it's a big jump. Okay, so that's unfortunate. That creates a less accuracy. Well, let's see. So this is the answer we got, and we compare it to the exact answer, which is pi. So you can see that the accuracy is certainly far from perfect because the exact is 3.14, and we have we have much less. We have a smaller number. Okay, so let me try to improve. That's not. I didn't realize that it would be so bad. So one way to improve it is just to go with with more intervals. Okay, so I'll try to have more intervals. Let me do the half of it. So half of, I'll go with 0.025. Okay. Okay. So let me fix this. This is 1. Okay, so it's better. So our estimate of half of the half of the circle is, as you can see, this is what I have at the top. I'm pointing at is the sum of the lengths of this of all this column of 40 entries, and it gives me 1.54, while the pi over 2, which is the precise answer, is 1.57. So as you can see, it gets better as we create more points. But you can see where the error comes from. Once again, at the very early, it is a very long step, and the long step is the problem with approximations is here. It is that we cut corners, right? So we go in straight while the curve curves, and that we always underestimate as a result. So inevitably, the result is far from very accurate, but it is at least I think it is more or less convincing that. With more work and making a bigger spreadsheet with more data, we can approximate the length with any accuracy that we wish. Okay, so as I said, the approximation done in calculus 3 is more accurate because it is based on the uniform distribution of points. And you can see I have a lot of points at the end, but they don't really contribute anything to the accuracy because we lose the accuracy early on, and that's we never really recover. So 1.54, 1.57, it's okay. It's good enough. So all right. So let's do it the right way now. This is the right way. That's fine. So that's not all we use here is the distance formula, nothing else, right? Look at it. One at a time. Just Excel did visualization for us, and it did the big heavy lifting of numbers, but nothing else. So it doesn't do any calculus. Just like with the areas computations, it's pure algebra. In the meantime, but if we want the answer with absolute accuracy, our sums turn into Riemann sums. Okay, so that's what we're after right now. How to compute, how to understand lengths of curves. The issue is the same as with areas under curves. There's a challenge there of understanding before you get to do computations. Okay, so so the question is how to understand and calculate lengths of curves. It's a big question, and it is, as you can see, it's a bit surprising. Maybe you noticed that we're doing it in the wrong order. We started with areas, and then we go down to lengths, even though the order of things is lengths, areas, volumes. Okay, in the dimensions grow and the complexity grows, but actually we did it the other way. So the areas first, that's the meaning of the Riemann sum, and now we're doing lengths all of a sudden. Lengths of curves. So the idea is certainly here was shown what we should do about it. However, there is one thing that we should be careful about in terms of using the analogies with the computing of areas and computing lengths. So it's the same curve, okay? So everything is the same, but what we are going to be approximating is either this area, so that's the area, or we're concerned with length period. So it's the same function. The starting point is the same. That's what we just carried out. I started with one spreadsheet that I used for computing the area, and then I tweak it a little bit with the same function. I just tweak it a little bit, the last column, in order to produce lengths. Okay, so there's a picture here that I hope explains the challenge, not the challenge, but rather cautionary tale is this. Okay, so a problem that I'm trying to solve is very simple, or two problems. My function is very simple. It is just a diagonal function, y equal x. Okay, so there are two problems we're facing. One we solved is the area. That's the image in the middle, and that's how it's solved. We approximate the area by putting those bars under the graph of the function, Riemann sums. So what I'm looking at in the middle is the Riemann sum. However, now, so then it might appear that approximating the function with the horizontal bars is the way to go, and that is the last picture. What if we are approximating my straight line with horizontal lines, like as if it is a step function? Okay, so do you see a problem with our approximation there?
Every step we lose one step of area.
No, we're not doing area anymore. The area works out. We did it. We confirmed that it works we confirmed it for triangles. You can verify it. We actually did it exactly that. Well, in calculus 1, confirmed that integration does produce, through Riemann sums, produces the area under the graph of a, say, straight line. This is a straight line. We can acquire that number, which is incidentally simply square root of 2. What is it? It's not the square root of 2. What is it? It's 1/2. The area is 1/2. Okay, even though we know it's from geometry, the area is supposed to be 1/2. So the point here is just to confirm that our method, which is Riemann sums, produces the result that we expect, and we did get the result as we expected. So if we make those bars and we make them thinner and thinner and thinner, at the limit, the total area will converge to 1/2, the area under the graph, that triangle. Okay, 1 by 1, half is 1/2. Okay, so that works out for Riemann sums. What the question is that arises is that with that experience, it might appear that it's reasonable to think about approximations of functions by as step functions. So that red, you see the red staircase, it is actually what we replaced our original function with. So the original function is straight, we replaced it with a staircase. It worked out with areas. What about lengths of curves?
It's going to be a severe underestimate because you're only taking into consideration your x dimension.
Right, so the actual length is square root of 2, right? The length of the diagonal, 1 by 1, square root of 2. What is my estimate?
It's going to be 1.
The estimate is 1. So if you only go horizontally little by little and count only horizontal ones, the length will be 1. So what does it tell you? Think about compared to what happened with areas. As we make those bars thin and thinner, the area gets better and better. What if we make those intervals small and small in the last case? What's going to happen to our estimate?
It should remain 1.
Right. It doesn't matter. Look at it. It doesn't matter how many steps you have. You still move from point 0 to point 1 horizontally only, and the result will be still 1. So it's not going to get improved. So every time you seemingly improve your approximation, you will be getting 1 and 1 and 1 and 1 every time, even though the answer you know is supposed to be square root of 2. Okay, so that's a big problem. What is the answer? As it was just suggested.
You have to use your y dimension.
Right. So a staircase, but you also want to include the vertical ones. Okay, so then what's the total?
Then it would be 2.
Okay, which is better?
Right.
But is it good?
No.
No. Why? Why not?
Because you're taking the total distance that is covered from each side.
Yeah, and so once again, you try to make those steps shorter and shorter, but the estimated distance still will be every time it will be 2. So there is no convergence. Your approximation will be always off by the same exact amount. So the square, you're never going to get square root of 2. Okay, so that is a mistake that is understandable, even though once we did it the right way, we actually did it with Excel the right way. And the right way is the distance formula. So you measure a straight line, you go straight. You don't go like this. Every time you go vertical then horizontal, you either get too much or too little, depending on those two options that we just saw. Either only horizontal or only vertical, that will be underestimate the distance by the same exact amount, or you go vertical and horizontal, then you overestimate by the same exact amount. And there is no convergence to the result that we want. But if we go straight, every time the distance formula will work out just fine. You just like this. Add those distances, and you don't even have to approximate anything. It is a straight line. So we just for as a cautionary tale of what could happen if we just choose the wrong tool to approximate things. And then the estimation breaks down. It is possible. Fortunately, we have the answer. Once again, every row here in the length column, they are exactly what is being visualized here. They are not horizontal, vertical, horizontal, vertical. These are straight edges. These are numbers given by the straight edges, just as they are visualized here. Okay, so and that, as we saw, works out. It also works out in this case when the whole thing is straight line, so that the problem is the solution is at hand, but it's not entirely obvious how that translates into an integral. Okay, because replacing estimations with absolute accuracy requires integrals, and we have to convert that sum that we just saw into integrals. And there is a tricky part there that is not obvious how to do it. Okay, so let me start to build it up. So the idea is the same. A partition. So we have function y equal f of x from a to b. Okay, we want to understand and calculate the length of this curve. So that's what I marked with yellow from this point to that point. Okay, well, let's try it. The approach is pretty much the same, so it will be approximation, but not with bars, but with edges. So like that shown over there. So if this is my curve, I will approximate, I will split it into smaller pieces, and then I will approximate my curve with a straight edge according to the distance formula. Okay, so we start with a partition of AB. So we have x naught is A, then less than x1, less than x2, less than xn, which is B. Okay, delta x is the same, xk minus 1. Okay, so which is the same as b minus a over n. Okay, so fine. Now, what does it do to us? For us, it splits our curve into n pieces. And if our delta x is small enough, then those pieces will be almost straight. Okay, so this is, let me zoom in on that picture. So we have xk minus 1 here, xk there. Okay, and then this is our curve going like this, possibly somewhere. Okay, and then what do we do with it? The idea is the same, coming from calculus 1 once again. We replace the something complicated with something linear and straight, and that is simply the edge. Okay, so all right, so the arch, or well, maybe the arc of the curve, so meaning that it is curve of the curve is approximated by the edge, the straight edge, and its length is, well, let's write out the formula. So this is y equal f of x. Okay, x is given, y is given, so let's just write out. Well, let me first say what it connects. So this edge between one point, which is what, xk minus 1, f of xk, that's the first point, this one. And then the second point is that one, and it is simply xk, f of xk. Okay, so these are the 2 points. They are connected by the edge, so I apply now directly my distance formula. So apply the distance formula. Okay, so the distance is, remember, subtracting x's squared, subtracting y's squared. Okay, so this is what we're looking at. So coordinate-wise subtraction. So I'll have xk minus 1 squared plus f of xk minus f of xk minus 1 squared square root. Okay, so that's the length of each segment. So is the length of kth segment, by which we have n segments, right? Look at the, if you take a look at our picture here, that certainly is clear that these are the edges. Okay, and you also can see that if we have enough approximations, it definitely looks like a curve. Okay, so the length of a case segment is this. So the total is the sum of these. The total approximate. I'm out of time, so we'll just finish it tomorrow.